So on page 1, example 2a, you have to look at the side measures. So if this is the smallest side measure, then the angle opposite that would be the smallest. So it's going to go angle F, and then angle H, and then angle G. The same is true for the angles. So when you get to example 2b, don't forget that you have to find the missing angle R before you can determine the side length measures. To determine if if triangles can have these side lengths, you have to take the two smaller numbers and see if it's greater than the third side. Remember, it can't be equal either. It has to be greater, and so this one is a no. And the explanation would be triangle inequality theorem. When you get to example 4 on page 3, the lengths of two sides of a triangle are 8 and 13. Find the range of possible lengths for the third side. So remember, the third side would be x. So you have to write your 3 scenarios. So 8 plus 13 is greater than x. 8 plus x is greater than 13. 13 plus x is greater than 8. And then you're going to solve all of these. One of them will cancel out because it'll be negative. So it's 21 is greater than x. And then this one, subtract 8 from both sides, and x is greater than 5. And it's a compound inequality, so we write our final answer as small number less than x less than big number. I'm going to skip over 5, 6 because there wasn't anything on the final related to this. For 5, 7, you're not going to have anywhere you're going to FOIL. So for instance, in example 1b, when we use the Pythagorean theorem, we would end up with x minus 2 squared plus 4 squared equals x squared. This x minus 2 squared is FOILing, so I'm telling you, you're not going to have any that result in that. So if that happens, you won't have to do it. So I know that now you try B, same thing's going to happen. So these are just a squared plus b squared equals c squared. So on page 13, when you have to tell whether it's a Pythagorean triple, you're going to do the Pythagorean theorem like normal. And if the numbers are whole numbers, no decimals, then it's a Pythagorean triple. So 14 squared plus 48 squared equals c squared. So that's 2500 equals c squared. And the square root of that is 50. So all of these are whole numbers. So yes, this is a Pythagorean triple. I'm on page 17 now, 5-8, special right triangles. So for the 45, 45, 90, remember that it goes x, x, x radical 2. And so we're going to get We were given 8, the leg, not the hypotenuse. So x is 8, and so this one's 8, and this is 8 radical 2. Once you get that one of them's equal, you just plug into the others, is what I should be saying. So 8, 8, 8 radical 2. So the side that they're trying to find, even though it says x, it's not really x from what we calculated. It's the one that's across from the right angle, and so therefore the answer is 8 radical 2. In example B, again, we're going to write out x, x, x radical 2. We were given the side opposite the right angle, so I'm going to write that that equals 5. And then I'm going to calculate that so I can solve. So x radical 2 equals 5. I'd have to divide both sides by radical 2. The shortcut is move the radical up above and put it over 2. But the real way is to multiply the top and bottom by radical 2. So we end up with 5 radical 2 over whole number 2. And those are both of our x's in that situation. Example 3 on page 18. It's a 30, 60, 90. And that is x, x radical 3, 2x. So we were given the side across from the right angle. So I'm going to put that that equals 22. And I solve that equation. X is 11. And then we plug in to the other two things. So 11 and 11 radical 3. So in the actual answer, based on what they wrote as x and y, x is the one across from 30 in this case, so x is 11. And then y is the one across from 60, so y is 11 radical 3.